Welcome back my dear friends, a very good morning, good afternoon, good evening wherever you are in this part of this globe. And this is the DADM 3 which is making 3 course under NPTEL MOOC series. And as you know, this course total duration is for 12 weeks. Hence, if you consider the contact hours, it goes into 30 hours. And the total number of lectures, as each of them are half an hour, each is in half an hour, the total number of lectures is 60. And this course, after each week where there are 5 lectures each for half an hour, you have an assignment. So, we have already wrapped up 2 assignments. We are in the 3rd week and you can see from the slides we are on 14th lecture. So, 14th and 15th should finish off your 3rd week, and after that you will have the 3rd assignment. Likewise, you will have till 12th week. So, 12 assignments, and after the end of this course you will have the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we were discussing the problem that given some constraints, and I was talking from the 2-dimensional point of view only. So, we will stick to that, and then later on try to give you how the overall simplex method or the algorithm works. So, in the 2-dimensional method, what is actually needed is you have a overall feasible region. And this feasible region technically has infinite number of points where you would basically have some value for the objective function. Why I am saying some value of the objective function? Because it will depend on the type of objective function you have. It can be either a maximization problem or the minimization problem. Now, these constraints can be of 3 types, would be for greater than type, less than type. For equality, obviously it would mean if the constraint by itself is equality, you would basically have only one straight line. So, the overall area to find out the feasible region would not be actually possible if all the constraints are equal to equality sign is there. So, if they meet at only one point, you will basically have one point solution. That means, the optimal solution is only one point. Now, whenever you are solving this this problem, the concept, if you remember, I mentioned, though very fleetingly, is basically you try to utilize the simple Gauss-Jordan elimination method. That means, the concept of matrixed solution technique is used to solve a set of simultaneous equation, but before that we will try to basically understand what is the logic based on which we proceed. This part of the lecture and the later part, which is the 14th and 15th, would be a little bit more algebraic in concept. The concept which we all know, we have studied in class 10 or below that. The matrix we may have studied later, but the concept of finding the solution of simultaneous equation is very simple. We all have done in before class 10. So, those would be utilized with some added on concept that how you will be able to get the feasible solution, or whether the feasible solution is possible, whether the constraints are applicable, whether the constraints are actually do have a feasible region, whether they are unconstrained solutions for that, whether they are unbounded solutions for that. So, all we will basically simply consider with simple diagrams, and then obviously come to the concept of that how you solve using the Gauss-Jordan method. So, consider the first part is that exceptional examples which are not a part and parcel of the solution, but you need to know that how they look like. So, what is this solution? So, I will tell you before the end result, and then tell you basically through the equations and the diagrams how it looks like. So, you will have unbounded solution here, that means the value of z is unbounded, which is the objective function. It can be either minimization or maximization. Maximization obviously we will consider, because we are considering inherently that x1 and x2 are greater than 0. So, they would always be in the first quadrant. So, obviously if x1 and x2 are unbounded, they can be negative also. In that case, you can have unbounded minimization problem also, because it will slowly go into the area which is basically the quadrant which is applicable for that. Considering the objective function is you are trying to minimize. So, obviously x1 and x2 can go as far as negative as possible. So, and that is point 1. Point number 2 is that, as you can see from the heading, it has got arbitrary large x values. X means basically the decision variables. So, they have got large x values. So, let us see the problem. The problem is you have maximization of z, which is 2 x 1 plus x 2, and the constraints are 2 in number. The third and fourth are very I will not say intuitive, they are very simple to understand, because as per the assumptions in linear programming, we will be considering all the variables to be greater than 0. Hence, the last set of constraints would be almost inherently considered whenever, whether you write it or not. So, the first constraint is x 1 minus x 2 is greater than minus 1, and the second constraint is minus 0.5 or half of x 1 plus x 2 is less than equal to 2. So, greater than minus 1 and less than equal to 2. The other variables which I said, the constraints are x 1 is greater than 0 and x 2 is greater than 0. Now, the concept which I am going to discuss need not be applicable for the 2 dimension only, it can go into higher dimension, but the reason I am trying to basically give this example is that it is easy for us to visualize how they look like when you solve the problem. So, here the actual answer is, when we see the solution you will understand, actual answer is I am giving you beforehand. Both the variables can be made arbitrarily large, infinite in value as z value increases. That means, x 1 and x 2 can be infinitely large, so would be the values of z, which is the objective function. So, let us see the overall feasible region and how the objective function looks like and how it moves. I am only drawing the first quadrant because that is where it is applicable. So, if you consider the first two constraints, the overall boundary region, I will basically mark it utilizing this colored pen. So, I will basically mark it using the yellow one. So, I am only considering the value of the first and the second combined together. So, if I consider x 1 and x 2 are not bounded, technically they would be here. So, all the region so this basically the whole area below that, which we will definitely consider the fourth quadrant, some part of definitely the first quadrant and the third quadrant. Now, you add up x 1 is greater than 0, that means it goes on to above the x axis, and x 2 is greater than 0, it goes on to the right of y axis. So, the moment you consider that, the overall feasible region now becomes, I will again use a different color. So, this coloring I did not do it in the diagram because I thought I will mark it as we solve the problem. So, all this area is there. Now, consider the maximization problem. So, in the maximization problem, if you place the objective function and where it cuts, I did not draw it, but if you use a simple Excel sheet, you will be able to do that. So, if you have the objective function, the green lines are the objective function, and as it is a maximization problem, it will start moving away from 0, more away from the 0 into the first quadrant. So, what happens? So, as I said, the boundary condition, the corner points would basically give you the objective function is maximum. So, the corner points are actually going towards infinity, hence z value also goes to infinity, which and how it is moving, the objective function is moving is basically the bold green line which you see. So, here you have an unbounded solution where the x value can be infinite and arbitrarily infinite values of x, which is x 1 and x 2 is applicable here. Next time. First, let us read what is written here. It gives you unbounded solution, but bounded x values. That means, one or more of these x's are such that they are not infinite, but the actual value of z is actually infinite. So, it may be possible that if there are two variables, one x is bounded, has a fixed value or not infinite value, but the actual value of the other x is infinite, hence the actual objective function which you are getting z is infinite. So, let us see what the optimization problem is. So, with respect to the first one, there also z was unbounded, here also z is unbounded, there all the x's were unbounded infinite, here some of the x's are bounded. So, in this case, as there are two variables, one is bounded, one is unbounded. Problem again maximization, again I am repeating why maximization, because we are only considering in the first quadrant considering the assumption being that x1 is positive, x2 is positive. So, maximization of z which is equal to minus 3x1 plus 2x2, and how you draw the objective function would immediately come out from the how the objective function looks like. x1 is less than 3, x1 minus x2 is less than 0, and as usual x1 is greater than 0, x2 is greater than 0. So, here note both variables need not be made arbitrarily large as z increases to infinity. So, let us draw the boundary region of the feasible the space, take the first two constraint. Now, in this case you have x2 is greater than 0, x2 is also less than 3. So, x2 greater than 0 would basically mean anything onto the right of y axis, x2 greater than less than 3 means anything, if you see my hand or if I point this pointer, anything onto the left of this, and the other constraint if you consider, it is the upper portion which you have. So, technically if I basically have the whole region, the feasible region, I will just mark it as it goes. So, whole region it will go along and there in the first quadrant. Now, objective function you mark, which is the green line, they are moving parallel. So, you want to increase the objective function value, because in maximization problem it keeps moving, but the corner point obviously you would always reach at infinite point. But remember one thing, x1 will keep increasing to infinity, x2 is fixed because it is less than or equal to 3. So, obviously the maximum value of x3 can be 3, which is a bounded solution. A solution means bounded value, but the z value if it keeps increasing, it will go higher and higher up. So, as x1 increase, x1 increases, the value of z also becomes infinite. So, here you have unbounded solution with bounded x values. Now, let us consider the case of a third example, where you have a bounded solution, but with arbitrarily large x values. So, that means the z value is bounded, it will have a maximum value, but the actual x values can be infinite. So, what is the solution? What is the objective function? Again the maximization problem, because you are considering only the feasible region which is applicable in the first quadrant, because due to the fact that x1 and x2 are both greater than 0 as per the assumption. So, the maximization value z is minus x1 plus 2 x2, and the constraints are x1 minus x2 is greater than minus 1, and minus half of x1 plus x2 is less than 2. So, these equations which I am drawing, please use Excel and draw it and double check what I am showing it exactly matches, because I am more interested to show you that how the feasible region looks like, how the x value are unbounded or bounded, and how the z value can basically be infinite or can be bounded. So, here both variables can be made arbitrarily large as z attains a finite maximum value where the value of z is 4. So, let us see how it is. So, have another look at the constraints. Constraints are x1 minus x2 is greater than minus 1, and minus 0.5 of x1 plus x2 is less than or equal to 2. That is the constraints. Obviously, other two being x1 is greater than 0, x2 is greater than 0, and you have when the maximization problem is minus x1 plus 2 x2 you have to maximize. Now comes the constraints. So, when you basically mark the constraints, so you have the region x1 is positive, that is obviously in the first and the second quadrant, but obviously this second quadrant will be ruled out because x2 is also positive. So, obviously any values onto the right of y axis, any values onto the top of x axis, and the common region which is there between the constraints would give you the feasible region. The feasible region is this one. So, I am trying to just mark it as clearly possible, it will go on to the right. Now, interesting fact is that when you draw the objective function, it is parallel to one of the constraints. So, if you see the green line and the bold arrow of the green line basically says that in order to attain maxima, it will should move up. So, where it crosses the feasible region is basically parallel. So, technically the z value is fixed, but the number of such combinations of x 1 and x 2 which will give you that value which is the fixed value of 4 is can be technically infinite. And if I consider the x 1 and x 2 value which will give me the same objective function which is 4 can basically go into infinity because any higher values of x 1 x 2 as I am moving my right hand more away from the 0 and going to the first quadrant far away from 0 would basically give you x 1 and x 2 being arbitrarily large and the z value is basically fixed at 4. The fourth type, which is an exceptional examples, is no solution with inconsistent constraints. So, what is the problem? Problem means what is the objective function? You maximize 3 x 1 minus 2 x 2, all these are maximization problem. I am repeating it time and again because you are only considering the problems where x 1 is greater than 0, x 2 is greater than 0 as per the assumptions. So, the first constraint is x 1 plus x 2 is less than equal to 4, and the second constraint is 2 x 1 plus 2 x 2 is greater than equal to 4. So, if you divide the second constraint by 2, you have x 1 plus x 2 is greater than 2. So, obviously, the region which you have to satisfy it is x 1 and x 2 is below 1, less than 1, and x 1 plus x 2 is greater than 2. So, here what, and obviously, you have x 1 is greater than 0, x 2 is greater than 0 as per the norm. So, here you have no solution exists as constraints are inconsistent. So, let us see that and let us draw the constraints and then see the concept that no solution is possible. Again, the overall region is given here. The first constraint which you have is this one. I am not going to mark it, I am just hovering my electronic pen here. So, it is less than 1. So, obviously, any area on towards 0 would basically be the area applicable for the first constraint. For the second constraint is greater than. So, obviously, it will be away from 0 on to the right hand side. So, this is there, but if I consider the common region between these two constraints, there is no common region. So, obviously, the constraints looks plausible, but the overall feasible region is not possible. So, the overall feasible region is 0. So, trying to find out any objective function which will whatever the objective function is there, but trying to find a solution is not possible because the constraints are inconsistent and they do not give you any answer. And obviously, it means that in this case also x 2 is greater than 0 means on to the right hand side of y axis x 1 is greater than 0 means above the x axis, but the common area obviously in the first quadrant technically, and obviously you will combine them with the first constraint and the second constraint. The fifth example, here no solutions with consistent constraints. So, the maximization problem is again a max of x 1 plus x 2, again a maximization because we are only considering simple examples where x 1 is greater than 0, x 2 is greater than 0. X 1 minus x 2 is greater than 0 and 3 x 1 minus x 2 is less than equal to minus 3, and as usual you have x 1 is greater than 0, x 2 is greater than 0. So, here the end result is, which I will show, is that no solution exists, but constraints are consistent as per the concept which is stated here. So, let us draw the constraint and see, and why we will see that no solution exists. Now, when I draw the constraints, the first two, So, the overall region, even though that is not the actual feasible region, because in the feasible region the constraint should satisfy that, and in this case the first last and the second last constraint, which is x 1 is greater than 0, x 2 greater than 0, are not applicable, because all of them, x 1 is greater than 0 and x 2 greater than 0, basically points to the first quadrant. But if you see the overall area common onto the first constraints only, this I will use a different color, because the feasible region I was using a light orange. So, I will use the color, say for example, light green. So, in this case of green has nothing to do with, say for example, the objective function which I am drawing. So, the common area between the two constraints is this one, but obviously the second and the third and the fourth basically do not match and give a feasible region. Hence, the constraints are applicable, are consistent, but the overall solution is 0 here. That means, you do not have any solution. So, that means no solution with even if the constraints are consistent. So, you have considered in the 5 different examples. In the first case, the x values can be arbitrarily large, similarly z values is arbitrarily large. In the second case, some of the x values are arbitrarily large, but some of the x values are not arbitrarily large. Still you basically have an arbitrarily large value of z. In the third case, we considered that the constraints were basically giving you a solution where the z value, the x values were infinite, but the z values was finite, which was 4. In the fourth case, you had a case problem or the type of error which you face, the constraints were inconsistent, hence there was no solution. And in the final case, which is in front of you, you saw that constraints were consistent, but the feasible region obviously was not possible, hence there was no solution. So, obviously, we may encounter such type of concepts in the higher dimension. So, it was easy for me to show that in the 2 dimension, hence I showed that with an example. In the problems which you are going to solve, that technically if the problem is a practical one which is solvable and the constraints and all the objective function are actually as it should be, then obviously the overall feasible region and the concept which we saw, this 5 may not definitely be applicable to this case, but I wanted to show you that these type of problems can occur, where the x and z's would definitely give you different sets of informations in the practical sense. Now, I will discuss before we go into the solution technique of the simplex method by Danzig. I will basically consider very simple algebra. It is nothing serious, it is very simple. Some of the definitions may be little bit involved, but I will try, and there is definitely no proof here. I am not going to consider any proof here, I will only explain it conceptually in order to make you understand. So, few of the properties. Wherever feasible solutions existed, the region of the feasible solution had what is in geometry we call the convexity property. So, hence the convexity property should hold true in order for us to find out the application of the linear programming using the simplest method, such that you will have a feasible region, set of corner points, and the corner points would basically lead us to the case where the objective function was either, when you are trying to maximize or minimize, would give you some feasible optimum solution. Now, what we mean by convexity, we all know that if a function is convex, you will basically have and if you consider lambda and you are taking a convex combination of the function, lambda is a value between 0 and 1 inclusive. Hence, lambda into f x 1 plus 1 minus lambda into f x 2 should be either the greater than equal to or greater than equal to the functional form of lambda x 1 plus 1 minus lambda x 2 in that case, and obviously for concavity it will be the different one. So, when the greater than equal to sign holds, it is strictly convex, and for a just convex function it will be only greater than for the case when it is convex function it is greater than equal to, and for strictly convex it is only greater than sign would hold true. So, this property means the region does not have any holes, such that when you are joining 2 points in that convex region, those points or set of points of the straight line which is joining them considering the convex region would always fall inside that region. So, I will try to basically give you a diagrammatic representation for that. So, again I am mentioning strictly convex and convex function or concave strictly concave function are from the conceptual point of view from simple mathematics, but how they look like considering the what is which has been mentioned. This property means that the region does not have any holes, that they are solid and there were no indentation in the boundary would also be made clear. So, let me make take a blank slide and explain it there. So, here it is. So, I will draw it. So, I will use the black pen. So, consider this area in 2 dimension. And consider this area. Consider this area, consider this area, or consider this area, or consider this area. So, let us go by one. This if you join any 2 points, I am use another color, join any 2 points, this is always inside the overall region. So, it is convex. So, let me put a tick mark. Use the red color, it will be easy. Till now it is fine. The moment it comes here, this goes out of the area. So, obviously it is not applicable. So, I will mark it. So, this is not done. So, hence I will put a blue color, no. Consider this area again. This is done, not done. This is done, not done. So, again I use the highlighter. So, this is not done, this is not done. If I use whether is applicable, no, it is not applicable. So, I will consider again these 3 diagrams in the corresponding 15th lecture. So, I will end it here and continue the discussion of what is feasible region and how it can be done. Have a nice day and thank you very much.